and where we're going with that and what the effect is on people's work. If that's the right topic, then let me know.
Yes.
Otherwise,
Yes.
wander off on other things. If that's okay.
That's okay. It's a great topic.
Right.
Thank you.
Okay, so first of all, the robots may be coming, but they're not going to take all of your jobs. If anything, I think we're going to encounter new jobs being created in consequence of artificial intelligence showing up. Historically, this has always been the case, where new technology has shown up. Some jobs are essentially eliminated through automation, for example, or they are eliminated through innovation. So as an example, if you were the maker of buggy whips, these are things you use to whip the horses and make them go faster. When the buggies are replaced by automobiles, you don't have a sensor on the automobile that you hit with a whip in order to make the car go faster. The people who built the automobiles had an accelerator instead. So the buggy whip guys, even if they lobbied for sensors that would respond to buggy whipping, didn't succeed. And so that business no longer was of much interest except for the few people that still ride horses. So that's an example of a situation where a product became obsolescent except for special purposes. That happens a lot. And the side effect of this is that some people, in fact, will lose their jobs to innovation. Then the question will be, what about the new jobs that get created? So in the case of the automobile, obviously lots of manufacturing jobs were created, design jobs were created, service jobs were created, even indirect jobs like creating roads for the cars to go on. That's a whole new imperative that was less important when people were riding on horses and buggies. So lots of new work. On the other hand, not everyone whose job was eliminated would necessarily have the skill set to do the new jobs. And so now we get into an interesting cycle where it's important for people to learn new things in order to stay relevant. And one of the things that we've learned in the Innovation for Jobs discussions is that we have several things happening all at the same time. One, of course, is innovation and new technology, new kinds of jobs being created, new needs being created, old ones going away, and a need for reskilling and relearning. The second thing that we observe is that there is another phenomenon which has been quite evident for the last 100 years or so, and that is that people's lives are getting longer because we're healthier, we eat better, we have better sanitation, we have better health care. A variety of factors have influenced life length or life duration. And so children that are born today may very well live to be 100 years old in the normal course of events. There are some implications of that long-lived period, and that is that over a period of a career of 70 or 80 years, lots of new technology will come along. A prototypical example of this is that only 12 years ago, the smart iPhone was introduced into the economy by Apple. And if you look now, you see billions of these devices, more than there are people. In fact, because a lot of people have more than one smartphone, have flooded into our environment. And they changed the way we do business. They changed the way we live our lives because of the ability of the smartphone to get access to all of the internet's resources and run apps and all this other stuff. So imagine that's just a 12-year period. Think about the rapid evolution and penetration of those technologies into our economy and into our social daily lives. Imagine now 70 years of technological revolution. I can't even begin to imagine what it's going to be like in 2089. And yet, our children will probably live through that, and our grandchildren. So the question is, well, what are the implications? And one of them is that you had better learn how to learn new things. In fact, you had better want to learn new things, because if you don't, you'll become irrelevant. So we can't do what we used to do, which is to learn for a while, and then earn for a while, and then retire. Now it's more like learn for a while, earn for a while, learn for a while, earn for a while, repeat. And so we have to teach people early in their lives how to learn new things and how to want to learn new things in order to stay relevant for a career that might last 7 or 8 decades. So that's an important element that we should keep in mind in the background while we think about the impact of AI. With regard to artificial intelligence, it's hyperbolic right now. AI and blockchain, which I don't want to talk about, are the two hot topics of the day. Artificial intelligence used to be about emulating what human beings could do. And this was sort of artificial general intelligence. That's not what we have right now. We do not have generally intelligent robots or generally intelligent software. What we have is narrow, very deep, but very narrow intelligence. And it's actually called machine learning, which is a particular kind of artificial intelligence. At Google, for example, we made very big investments in machine learning concepts. The notion of a neural network, which sort of emulates what goes on in your head, at least structurally speaking, has become quite powerful because the early development of these neural networks about 50 years ago in the 1960s was sort of a single layer of neural structure. We had these artificial neurons or emulated neurons that had connections to other neurons inside this one layer. And they had weights associated with them. So inputs would go into the top and something would come out the bottom, a decision, identification of an image or something. And they didn't work very well. And in fact, two very famous guys at MIT, Minsky and Papert, wrote a book called Perceptrons, which was a particular kind of single layer neural network. This book said they don't work. And for some decade or so, or maybe even more, the whole area of researching into neural networks kind of collapsed, except for a few people who persisted. But then about, maybe a decade ago, or maybe a little less, there was a renewed interest in these neural networks because we found a way to make them hundreds of layers deep and still run efficiently. In fact, new hardware was developed in order to make those deep, heavily layered neural networks function. And in the course of making multi-layer networks work, we discovered that they could be trained by exposing them to inputs and then telling them whether or not their decisions were correct or not. So imagine for just a moment, you have a couple of hundred layers worth of these things. Each layer has emulated neurons in it that have weights associated with them. So when the inputs come in to the top, weights are associated with the inputs, and they're connected and computed and pop out the bottom going to the next layer. And you start out with just a random set of weights. And so you say, show it an image, and you say, what is this? Is this a cat or a dog? And it says it's a dog, and you say, no, it's a cat. And so it says, okay, so I got a negative answer to that. The protocol causes the error, that is to say you got the answer wrong, to propagate back up through the neural network to change the weights to get the answer closer to the answer that was desired. That's called supervised learning. Another form of neural network is called unsupervised learning, and that's where you just present it with an image, for example. You present it with an input string, or you present it with a sound or something like that. And you let it separate things into different categories in an unsupervised way. This is a pattern discovery process. So those are two kinds of ways of training the neural network. We had extraordinary success with some of our early networks built by a company called DeepMind, which is one of the alphabet companies, of which Google is also one. So there's Alphabet has a dozen or so companies. Google is one, DeepMind in London is another. They designed a multi-layer neural network system to play the game of Go. This was like 3 years ago. And they trained it by having it play with very good Go players. And then eventually it even had it play with itself, different versions of the same game. Mm-hmm. And at some point they decided to have a public contest with an established grandmaster of Go, a man named Lee Sedol in South Korea. And the computer program, the Go, AlphaGo was the name of the program, won 4 out of 5 games from Mr. Sedol. And that was fairly shocking for everybody. And in fact, although I'm not a Go player, I can give you a secondhand observation. In the first game, at move number 37, apparently this was a move that nobody had ever seen before or anticipated. And all the Go players are saying, what's that? Why did you do that? This is nuts. And later, it turns out, if you look back, you discover that move number 37 was crucial to winning that particular game. And of course, everyone is saying, how did you figure that out? And the answer is nobody exactly knows how it figured it out, which is a problem with this kind of neural, artificial intelligence. Sometimes we can't figure out why it does what it does. All we know is that we ran it through all these training sessions and it produces a result. This causes a certain amount of concern for people, not so much about playing games, but what if it's making decisions like, is this a cancerous cell or not? Is this image an example of a cancerous cell? Or should this person get a loan from the bank or not? Or should this person be released from prison or not on probation? If you don't understand why the system makes the decision it does, it causes a lot of discomfort. And so you're starting to hear people say, I don't want us to use these kinds of artificial intelligence methods unless you can explain what the results are. And so this is putting a lot of pressure on my company and others to understand more deeply how these systems actually work and why they produce the results they do so that we can decide whether to trust them or not. Which brings up another issue. It's called implicit bias or built-in bias. When we train these systems, we have to present them with some kind of content which is relevant to the decisions that they're going to be making, whether it's a classification system or a decision about choosing to do an A or a B choice, give a loan to this person or don't give a loan. So the training sessions are intended to get the system to put the right weights into the neural network to make the right choices. The problem is, what if the training data is biased in some way? So to give you an example, in the American legal system, criminal system, there is an inordinate bias against people who are black, because more of them end up in jail, and for all kinds of reasons. And so the result is that there appears to be a high recidivism rate because you seem to have more black people in jail than white people. So the system that was trained to help make a decision, should we allow this person out on probation, was biased against black people. And this was not obvious until somebody pointed out that the results were really unacceptable. And so now we realize that there are lots of ways for these artificially intelligent machine learning systems to become biased by the training information that they're given. So now we have to figure out, how do we detect bias in the training data so as to eliminate it? Again, another big issue, and a warning not to rely on systems like this without understanding more deeply how they work. This raises yet another interesting question, and it has to do with brittleness in the system as opposed to bias. What's that all about? Well, it turns out that, for example, let's take the classification situation where you are exposing the neural network to all kinds of images of different animals and other kinds of images, cars, trucks, and things like that. And you're asking it basically to classify the images that it's seeing. So group all the cats together and group the dogs together and the kangaroos and the fire trucks and things like that. And so the idea is to present it with an image classification task, and it's supposed to tell you what image it's seeing. So we do this, and we get a neural network that does a really good job of classifying these various things. You show it a dog, and it says it's a dog. You show it a cat, it says it's a cat. Then you go in and you change just a few of the pixels of the image, and maybe just 2 or 3 pixels in a 10,000 pixel image, 100 by 100 image. And suddenly, and you present that to the neural network, and you ask it, what is this? And it says it's a fire truck. Now, we look at this and we say, no, it isn't, it's a cat. These 3 little pixels didn't make any difference in the way we perceive this image. And so your first reaction to this is, how the hell could it possibly think this is a fire truck? Okay, so now we have to have a little tiny tutorial here for a second. We're going to pretend that you're actually all mathematicians and that you're familiar with linear algebra. Okay, there'll be a final exam on Friday, by the way, just in case Guido didn't tell you this. So I want you to imagine for a moment just a three-dimensional space, right? The one that we live in, right? There's up and down, and there's left and right, and there's front and back. So there are three, I don't know if I can do this on the figure, there are three vectors here. And imagine that any point in this three-dimensional space can be represented by what's called a vector. And the vector just has three values, the x value, the y value, and the z value. And those three numbers say where the point of the vector is. And if you change any of the numbers, that point on the arrow, the vector, moves around in the three-dimensional space. So everybody can visualize that because we live in the 3D world. Now I want to leap into a much bigger dimensional space. So let's take an image that's 100 by 100 pixels, and just think they're black and white for a moment, just for simplicity, which means that each of those pixels in the image, all 10,000 of them, have a value of either 0 or 1. Just or 1 and 2, it doesn't matter, just two different numbers. That means that in a 10,000 dimensional space, the image is a vector with 10,000 different numbers associated with it. Now, I know, you can't quite visualize that, but imagine that if you change a pixel, it changes just one of those 10,000 numbers, and so that 10,000 dimension vector moves around in the 10,000 dimensional space. When the system is trained to do images, image recognition and classification, all the dogs end up in a certain 10,000 vector direction, 10,000 dimensional direction. The cats are in another 10,000 dimensional direction, and the fire trucks are in another one. So when you finish the classification and training, what's happened is that you've created what are called hyperplanes in this 10,000 dimensional space that separate the cats, the dogs, the kangaroos, and the fire trucks. Now I want you to imagine what happens to those vectors, those 10,000 dimensional vectors. When you change 1 or 2 pixels in the image, you're actually changing the numbers that are associated with the 10,000 dimensional vector. And when you change a number, the vector moves around a little. What if it moves past a hyperplane that separated the fire truck from the cat? That's how you end up mistaking a cat for a fire truck, because the vector has moved just slightly because of these changes. Well, if the people who study these things have even developed artificial intelligence machine learning systems that will try to fool the other system on purpose. And so we set these things against each other. The one guy is twiddling bits to try to get the other guy to get the wrong answer. And so we call these generative adversarial networks. And that's how we discovered the possibility of this brittle failure to do the classification properly. And why do I tell you all this? Well, partly because I wanted you to think about, high-dimensional vector spaces. But I also wanted you to recognize how difficult it might be to realize that you have a multi-layer neural network which has this brittle property in it that it might misclassify things. And so now another challenge that we have, if we're going to use these techniques, is to anticipate and maybe even try to analyze and identify the potential for this brittle failure. If you don't do that, you're going to end up with decision-making and choices and actions that turn out to be surprising and often wrong, and therefore potentially very hazardous, especially if it's a self-driving car that may be using these neural networks to decide whether it should go through the traffic intersection. Does it know where the red lights are? Does it know if it's a red light or not? What if it gets that wrong for some reason because it's been confused by some other light that's in the field of view? That would be a bad thing. So I want you to understand that these technologies are not perfect, and therefore we should be very thoughtful about how they get applied. If I could, I want to make one other observation, which is outside of the basic artificial intelligence box, and more generally deals with software. All of you, I'm sure, have heard the term Internet of Things. I'm sure Guido may have mentioned it in the course of some of his briefings. These are just devices that have software and programs in them that take inputs from the outside world, sensor input and things like that, and then do something with it. So if it's something simple, like a heating, ventilation, and air conditioning system, it takes temperature information in, and it decides how to adjust the heating system to reach the desired temperature. Those systems are just plain software. There's nothing magic. It's not artificially intelligent. However, one thing that you might have noticed about programmers is that they don't know how to write software that doesn't have bugs. Those are mistakes. And apparently we've gotten away with murder. I used to be a programmer. I made my living writing software, and I'm embarrassed to tell you I made a lot of really stupid mistakes. And often they would show up in the program doing the wrong thing, and when you go to look to see why did it do that, you discover you did some dumb thing like checking a variable that never got set, so you got a random answer, or you miscalculated the amount of input that was coming in, and you had what's called a buffer overflow, and it clobbered part of the computer program that you were supposed to be running, where you made a reference to an array and you were off by 1, so you got the wrong answer. Those are really stupid mistakes, and I think most programmers have a little dent in their forehead where they've slapped themselves for making a dumb mistake. The later say, so how could I do such a stupid thing? The problem we have is that there are a lot of pieces of software now, especially in these Internet of Things devices, that we're relying on to do action autonomously. You know, there's no human in this loop. It's just taking inputs, making decisions, doing some kind of control. So we should be very, very concerned about the quality of software that we rely on, independent of artificial intelligence. That's a very important problem. Last point to make is that now that I essentially argued that you should run away from all this stuff, in fact, these systems can be extremely powerful and extremely useful. So I'll give you an example that surprised us at Google. We designed a multi-layer neural network to manage the cooling of our data centers. So somebody said, you know, every week, some poor human being looks at how well we have done the cooling of the data center, how much power was required to run the pumps and to run, to get cold water to run through the system to cool the data center properly. And once a week, somebody would adjust all the variables in order to try to reduce the amount of power that was required to cool the data center. That would reduce cost. Somebody said, why don't we train a multi-layer neural network to do the same job? So people said, well, I don't know if that would work, but they tried. So they, for some, I don't know how long, this may have gone on for some weeks, they had the system taking all the inputs about how was the temperature. Oh, I'm sorry about that background noise. It'll stop in a minute.
That's a long way.
Ringing. I apologize for that.
That's a telephone.
One more ring. One more ring and then I should have taken the phone off the hook. This is probably a political
The
call.
phone
Right
off the
now, we're in political season in the U.S., and these are people asking for money. So here we are. I've lost my train of thought. What were we going to do? We were trying to get to
Cooling, data center.
Cooling bit.
Sorry?
The cooling.
No, the cooling system. Right. That's fine. Anyway, we trained this system to take in all the inputs from the controls, or how the valves were set, how fast the pumps were running. And then our metric of success was reduced power requirement in order to keep the data center cool. So that was our important metric. So we trained this thing, and then we turned it loose to run the cooling system, and it reduced the power requirements by 40%. 40%, not 4%, 40%. Astonishing, completely unexpected. Of course, then we ran off to do that with all the other data centers. The point here is that these systems can be extremely powerful because of the ability to absorb huge amounts of input data and to analyze it in this very implicit way. So at this stage of the game, at Google, we're injecting a great deal of machine learning into a lot of our products and services. Our machine translation systems use neural networks, multi-layer neural networks now, and not pre-statistical mechanisms for doing all this. So at this stage of the game, we're very heavily invested in this sort of machine learning. looking for new ways to apply it in a variety of applications. So I stopped there. I think we agreed that I would go on for about 20 minutes, which I've done, and now I'm happy to answer.
Thank you, Vint. We have a very tight program, so we have a few questions. So where is the boom microphone? Yeah. I go to Vincent first. You met Vincent before?
Yeah, from the EZOC Society Netherlands. Hi, Vincent Evers. Hi, Vin.
Yeah. Hello, how are you?
Yeah, I'm alive and kicking. I'm going to send you an email. But thank you for this College 101 on artificial intelligence. Now, of course, we want to know how we get a more people-centric economy. How can we use AI to make the economy more people-centric? So what is your solution for that?
Well, I'm not sure I will argue with the solution, Vincent, but let's think a little bit about the heart of the people-centered economy, and that is trying to make people more useful and more valuable. And the way to do that is to try to put them into jobs where their strengths are, in fact, best exercised. There's a company that does this now, it's called the Gallup Company, and they have a program they call Strength Finder, which some of you might have heard of, and it tries to evaluate people's skills and strengths, what is it they're good at. And once you have the answer to that question, then you can ask yourself, okay, if I have a set of work to do, how do I cut up that work so as to fit the people into the work that is best suited for their strengths? So instead of jamming people into a particular job, what we want to do is shape the job to fit their strengths. And then in the end, of course, you want to be able to figure out how to cover all of the work that needs to be done by fitting people into this matrix of work. Artificial intelligence and machine learning might actually help us figure out how to do that. I don't want to overstate the case, but if you think about we're back in mathematics again. You know about tessellations are ways of covering a plane area with some pattern, and so that every part of that plane area is covered. So imagine a simple grid. That's a tessellation. Imagine a set of triangles that equal out of the triangles. You can fit them all together so they cover an entire space. Imagine for a moment now that we have this very irregular shape which represents your strength to do certain kinds of work. What we want to do is take a collection of people with their strengths and figure out how do we map them into this space of work so that everybody ends up doing the things they do best and we still cover all the tasks that need to be done. That's an example of something that might be solvable using machine learning techniques. I don't want to overstate the case, but it's the sort of the direction that I would be heading in, given the results that you've had with other machine learning exercises where some very surprising optimizations have emerged from that technology.
Thank you, Vint. We go to the second question here. Can you please say who you are?
Yeah, hello, Vint. My name is Louis de Bruin.
You have to look there.
I'm
No,
working.
no, no,
look
camera's
there.
off.
Look at the camera.
Don't worry.
You look at my back, sorry about that. The question so Louis de Bruin, I'm working in a topic that I'll mention in a moment at IBM. And it's a topic you don't want to talk about, blockchain. Now, I'm not going to trick you into talking about blockchain because I can't, but I'm very interested why you don't want to talk about it.
Yeah, thank you. I actually appreciate the question. My big worry about blockchain, first of all, is that everybody says it's a solution to everything, which is the top of the hyperbolic curve. So let's set that aside. My worry about blockchain generally is, first of all, that it takes time to form the consensus that's needed to decide who signs the next block. And there are a variety of ways to do that. The Bitcoin version of it involves mining, which is very heavily compute dependent and therefore electricity dependent and so on. So I'm not a big fan of that. I worry about the rate at which blocks can be formed in order to use the blockchain to handle high transaction rates. And I'm not persuaded right now that the high transaction rate cases work very well with the current blockchain algorithm. I also understand there are some people that are trying to build a kind of hierarchical multiple blockchain system, maybe putting the blockchains into a Merkle tree so that you end up with parallel blockchains taking on different transactions and then trying to weave them together. But I'm still a little skeptical on how all that will work. The second thing that I find uncomfortable is this anonymous blockchain idea. Now, people will run around telling you that because of the anonymity, everything is wonderful, and you don't have to rely on anyone, you don't have to trust anyone. The implicit assumption there is that because everyone's anonymous, you should be able to trust them, and I don't buy that. I actually prefer a permission blockchain if I'm going to use this at all, so I know who it is that I'm trusting and why am I trusting them. So I prefer a permission blockchain to the anonymous one. So those are a couple of the reasons why I'm a little skeptical of blockchain. I will tell you, however, we use blockchain at Google for certain applications where the transaction rates are low enough that we aren't worried about the rate at which the blockchain signatures can happen. And of course, in our case, we're in complete control of that particular application, so we know that we're trusting ourselves and nobody else to do that. So I'm not a total skeptic, but I am a little concerned about overselling of that particular technology.
Vint, thank you very much. We need to switch to Dutch and talk to the audience here. Thank you for being with us. Ik haal even mijn